Chapter 3. Explanation of phenomena related to the propagation of rays. The force caused by the traveling groups of Yaldons. Normally, the forces are balanced around all the molecules or atoms in a substance with a rectangular shape, excluding the corners. This is due to the incoming bombardment from the traveling groups of Yaldons onto all sides of the substance. A location where the resultant forces are different in a substance is on the surface molecules of a liquid or solid substance. For example, if a solid substance is placed in an environment with air, gas, then the molecules on the surface of the solid substance will oscillate with a greater displacement than the molecules below the surface. Following will be figure 3.1 representing the forces between the molecules with springs. In fact, there are no springs between the molecules of any substance, but the nature of the forces between the molecules and/or atoms behaves as a spring. Figure 3.1. A rough diagram representing the forces between the molecules. The molecules below the surface of the rectangular solid will have balanced forces acting upon them. The forces between them are represented by springs with a constant K. When any substance is placed in a less dense medium, as in figure 3.2, the traveling groups will strike the surface molecules of the more dense substance from all directions with varying angles. The area, A sub s, will represent the cross-sectional area of one molecule on the surface of the more dense substance. Then that cross-sectional area, A sub s, will be under a constant bombardment from the traveling groups with different angles of alpha in respect to the y-axis, and each hit from the traveling groups will apply a force that can be analyzed into two components, F sub pxz and F sub py. The value of the two components will depend upon the angle of incidence alpha and the momentum of the incoming group. Following will be figure 3.2, which will illustrate the resultant force, F sub py, applied perpendicularly into the surface molecule, molecule A, from the continuous bombardment of traveling groups. Figure 3.2. A rough diagram representing the resultant force, F sub py, on the surface molecules from the incoming traveling groups. The component F sub pxz will cancel each other out, since the traveling groups will hit the cross-sectional area, A sub s, from different directions and varying angles in respect to the y-axis, as seen in figure 3.2. As a result, the only component that will act on the surface molecules is the force F sub py, and this force causes the surface molecules to vibrate vertically along the y-axis. An example to relate this concept to is a trampoline. The components F sub pxz can be compared to the springs which hold the trampoline taut in the horizontal direction. As a result, the surface of the trampoline will only be able to move in a vertical direction. As well as oscillating vertically in the direction of the y-axis, surface molecules will also have a larger span of oscillation than the rest of the molecules that are internally within the dense substance. Following will be figure 3.3, which will represent the cancellation of the forces, F sub pxz, on molecule A as the traveling groups bombard it from different directions and angles. Figure 3.3. A rough diagram showing the components of F sub pxz applied to molecule A on the plane xz, due to the strikes from several traveling groups onto the surface molecule. The traveling groups also strike molecule A, seen in figure 3.2, from the opposite side, the side of plane xz that is toward the internal structure of the dense substance. But the rate of the traveling groups coming from that side will be less than the rate of traveling groups which come from the less dense medium. This is due to the more dense substance totally reflecting the traveling groups that strike the surface at an incident angle alpha, which is more than the critical angle, see figure 3.2. Then the force F sub py is a resultant force from the bombardment of traveling groups onto both sides of the surface molecule A. The critical angle of reflection does not only apply to visible light, but also to traveling groups of Yaldons. The differences are the traveling groups of Yaldons do not have a periodic displacement between them, and each group will travel in a non-uniform random direction. Thus, the traveling groups of Yaldons will not be considered as a propagated ray. Larger molecular structures will be under a higher rate of strikes from the traveling groups since they will have a larger cross-sectional area. As a result, there will be a stronger resultant force of F sub py. Then the surface molecules of that substance will have a greater span of oscillation when placed in a less dense medium. For example, the molecular structure of a diamond is larger than glass. Then the surface molecules of a diamond will travel at a greater distance from the surface as it oscillates, when compared to the distance that the surface molecules of a glass travel. The greater displacement of the surface molecules in a diamond will give it the characteristic of being able to scratch the surfaces of other solid substances. Also, this vertical oscillation of surface molecules caused by the resultant force of F sub py from the bombardment of traveling groups will not allow a broken substance to be placed back together. Tearing a sheet of paper in half is an example of this effect, since molecules on the new surface, where the tear happened, will swing farther than they had prior to being torn apart. The span of oscillation on the new surfaces will be too great when compared to the small distance required to maintain the forces between its molecular structures. As a result, the surface molecules of the sheet of paper will no longer be able to be placed back together again after being torn apart. Breaking a piece of glass in two parts is another example of the surface molecules oscillating at a larger distance, greater span. The two pieces of glass will no longer be able to be placed back together due to the effect from the larger span of oscillation produced by the molecules on the new surfaces. Total reflection. The forces between the atoms or molecules of any substance can be represented by springs with different values for the spring constant K. The value of K will depend on the type of substance or element. Different substances will have different values for the spring constant K. See Figure 3.1. When one propagated group of light strikes the surface area, A sub S, as in the following Figure 3.4, with a force of F sub I can be analyzed into two components. Figure 3.4. A rough diagram representing the components of forces acting upon the surface molecule as a propagated group of light strikes it. The component force, F sub Iy, will compress spring Sp in the figure above. There will be a distance of compression, S, and a required rate of time for the spring, Sp, to store the kinetic energy from the impulse of the incident ray group as potential energy. When the spring, Sp, expands, it will apply a force equal to F sub Iy, but in the opposite direction, at an angle of 180 degrees, as seen in the figure above with the force F sub Ry. This is due to the surface molecules oscillating in the vertical direction in regard to that surface. Then the incident ray will reflect in the direction of the force F sub r at an angle equal to alpha in respect to the y-axis as seen in the figure above. This force, F sub r, is a resultant force from the components F sub ry and F sub ix. This will result in a total reflection for the propagated ray, incident ray. The kinetic energy, E sub Ki for one propagated group from the incident ray is, where m sub g is the total mass of Yaldons contained in one propagated group. In order to have total reflection on the surface of any substance, the value of the constant K must be large enough to store the kinetic energy from one propagated group of the incident ray. Following will be a diagram and formulas modeling this concept. Figure 3.5. A rough diagram showing the reflection between the force and momentum of one propagated group from the incident ray. Hooke's law. Multiply both sides of the equation by ds, taking the integral of the upper and lower limits. The limit of 0 is the point where one propagated group meets the surface molecule, and S sub max is the displacement of the surface molecules due to the energy received by the same propagated group. If the value of the constant K for the spring Sp, see Figure 3.4, is not large enough to provide the potential energy E sub Piy equal to E sub Kiy from the force F sub Iy, caused by the incoming propagated group of the incident ray, then the surface molecule from that substance will not be able to provide the force, F sub Ry, needed to reflect that kind of incident ray. As a result, this surface will be a black or transparent surface. The frequency of the surface molecules will determine the color. Some surface molecules can synchronize with a wider range of frequencies from the incoming rays and will reflect more than one color. This can be seen in equation 210, which is dependent on the natural frequency of the molecules, F sub m, and the frequency of the incoming propagated rays, F sub p. When the molecules on the surface of a solid or liquid cannot provide a perpendicular force, F sub ry, that is equal to F sub iy, then the surface will be black or transparent. For black surfaces, the molecules under the surface will not be able to resonate with the frequency from the incoming propagated ray. The Yaldons in that incoming ray will be scattered among the molecules of the black substance. Then the total amount of Yaldons will increase among the molecules of that substance, then the conservation of momentum will allow in the universe, m sub y. As a result, the extra amount of Yaldons will be radiated as heat as the traveling groups bombard the black substance's molecules. In the case of transparent substances, the molecules under the surface will be able to resonate with the frequency from the incoming propagated ray. Then the molecules of the transparent substance will be able to propagate the incoming light ray to the opposite side of the transparent substance. The transparent substance will be considered as a conductor for the propagated groups of visible light. But the propagated groups of infrared will not conduct with the molecules of a transparent substance in the same manner as visible light. Then this substance will be considered as a semiconductor for infrared. Refer to equation 210. The refraction of propagated rays. The surface molecules of transparent substances will not be able to provide a force that is equal to F sub Iy. Then the force F sub Iy will be added to the force F sub Py, resulting in F sub Pi as shown in figure 3.6 below. Figure 3.6. A rough diagram representing the angle of refraction, R, in a transparent substance. The angle R in the figure above depends on the force F sub Py, and F sub Py depends on the size of the surface molecules. A sub S will be the cross-sectional surface area of a surface molecule, see figure 3.2 and 3.3. According to figure 3.6, then the sign R will be inversely proportional to F sub Ri. After substituting the proportional value of F sub Ri into the relation sign R, according to equation 2.9, the velocity of a propagated group in a transparent substance. After rearranging the variables, according to the above, the velocity of light in a transparent substance will be inversely proportional to the size of the surface molecules. Then, after substituting the value of from relation 3.5 into 3.4, according to the relation above, the velocity of the propagated ray in a transparent substance will be proportional to the angle of refraction, r. The surface molecule will follow the direction of the resultant force, F sub Ri, while oscillating about its rest point, and the propagated ray will move in the same direction of that force, F sub Ri, see figure 3.6. The traveling group of Yaldons will apply a balanced force on all molecules of that substance, except for the molecules located on the surface and near the corners. Since the rectangular transparent substance has parallel sides, then the emitted Yaldon group will keep moving in a straight line within that substance, since there is no force component of F sub Py on the internal molecules, until it reaches the opposite side, where it will come into contact with another surface molecule. That surface molecule from the opposite side, as seen in figure 3.7 below, will be under the force F sub Ro. The force F sub Ro has two components, F sub Oy and F sub Ox. The force F sub Po will equal F sub Oy minus F sub Py, and the resultant force, F sub O, will be the final force with an angle of beta. The angle of beta will be the same angle as alpha from figure 3.6 and figure 3.7. Figure 3.7. A rough diagram representing the propagated rays passing through a transparent solid substance and their force components on the surface molecules. The force F sub RO equals the force F sub RI, since the transparent solid substance will maintain the momentum of the propagated ray through all its internal molecules. According to the figure above, F sub OX equals F sub IX, and F sub PO equals F sub IY, since there is a force F sub PY that has the same value applied onto both surfaces. Then the tangent of beta equals the tangent of alpha. As a result, the leaving propagated ray will be parallel to the incident propagated ray.